Hi everyone, welcome to our final presentation of EE599 Deep Learning. My name is Yao Qu, a second-year master student of electrical engineering in USC.
And I'm Wenjun Guan, also second-year master student from ECE department. Our project is image style transfer.
Our presentation will include background-related works, our model architecture and training detail, experiments and results, with conclusion.
What's the image style transfer? Style transfer is a technique of separating and recombining the content and the style of an arbitrary image. And the final predicted image involves both the photo's content information and the artwork style information. As this picture shows, the algorithm changed the content image, which is the gate, into a colorful oil painting.
To realize this style transfer goal, we read many papers. The first and most popular one in this field was introduced in the paper Neural Algorithm of Artistic Style in September 2015 by Gaddis, and then Gaddis published this image style transfer using convolutional neural networks in 2016 to show how to use stochastic gradient descent to deal with this problem. In this paper, Gaddis just used one VGG16 night, and here is the mean night. The key idea behind this algorithm is to iteratively optimize an image with the objective of matching desired CNN feature distributions. This model is known as neural style transfer.
In March 2016, a group of researchers from Stanford University published a paper which outlined a method for achieving real-time style transfer. The paper, titled Perceptual Losses for Real-Time Style Transfer and Super Resolution by Johnson et al., shows that it is possible to train a neural network to apply a single style to any given content image with a single forward pass through the network. And here is the main idea and neural nets of Johnson's paper. Also, we use this architecture as our primary idea. The model is known as fast style transfer, since once you finish training the model, you can get the output image thousands of times faster than neural style transfer. Several loss functions are defined in our project to measure the differences between output image, content image, and style image. The goal is to minimize the loss during training process and get the best performing model. First, we have feature reconstruction loss, which extract the feature representation. Then, define the graph matrix as following. Use graph matrix and squared Frobenius norm to represent style reconstruction loss. Also, define the total variation regularization as this. Then, we say the output image y hat is the argmin of each loss times a specific parameter. In our experiment, we find that the best hyperparameter pair is content parameter equals 2, style parameter equals 3, and TV width equals 5 times 10 to 5, 10 to minus 5.
We also use residual block in the middle of our transform night, which can help to decrease the information loss in deeper layers. This is the detailed architecture of residual block we use in our project. It used the batch norm, and the activation function is ReLO in this case. Using residual block is important in our project as the output image should share both features from style and content images. For our project, our method is divided into two processes. First one is to train a model on a given style image, and second one is to apply the style to any given image in only one forward pass. At the beginning, we do the pre-processing of input image and with this input size. Then we construct convolutional 2D layers, and after residual block, we have convolutional 2D transpose layers. Finally, we do denormalize and get the output generated image, which has the same size as the input. We use part of Microsoft COCO dataset as our training data.
VGG is a convolutional neural network model from very deep convolutional network for large-scale image recognition, with 16 layers of CNN and ANN, involving 138 million parameters. We use it as our feature extraction network. We compute the feature reconstruction loss at the layer marked as the blue rectangle in this frame, and style reconstruction loss at 5 layers of the VGG16 network, which is marked in red in this frame row. The training process is done as follows. The first step is given the image, which is the content image from the COCO dataset, to the image transformation network to get the generated image. Then, give the generated image to the VGG16net to get its content and style representations. The third step is to give the same image, which is the content image, that was given in the first step from COCO dataset to VGG16net, also to get its content and style representations.
Then we need to compute the style loss function between the style representation of the generated image and the content image. We still need to compute the content loss function between the content representation of generated image and the content image. We need to compute the global loss function, which is weighted sum of the previous two losses. And then we need to update the weight of image transformation network with respect of the global loss function. Finally, we need to repeat the previous steps on the whole dataset until the style transfer process is done very well, which means the global loss is minimized. We use such a follow of USC as our content image, and there are style images.
We try to optimize our CNN architecture and parameters. Firstly, we try to change size of training dataset from around 10,000 to 20,000. We found that with more training data, we have more features of content can be maintained.
Then we want to change the number of epochs, and here is the comparisons. We can find that more details of content can be maintained with more epochs.
To realize downsampling, we use two methods: stride two convolutions to downsample and use max pooling to deal with this problem. We found that max pooling makes the color contrast more vivid.
Also, in our transformation net, we changed number of residual block and found that more details of content can be protected with less residual block.
When we change number of convolutional layer, we found that more features can be shown in less convolutional layer case.
Here is Getty's only VGG16 results from the same content image and style image. We trained for 10 iterations for each output, and it used about 10 minutes on AWS.
This is the comparison of our modified fast style transfer model versus the original neural style transfer model. We can see that NST has better content details extracted, while we have better style maintained. If we use the whole Microsoft COCO dataset and trained for more epochs, we will definitely have better results. However, due to time and cost limit, we can't afford that, and we want to explore more on parameter tuning and architecture modifying.
Finally, we use our model and try to deal with black and white photo as content image. We found that our deep learning model can also help to colorize the black and white photo. This is the conclusion we obtained from the experiments and explorations on the model from our final project.
Thanks for listening.